Welcome everyone to the British Interplanetary Society West Midlands branch meeting. Still admitting people. Just a reminder, we are recording this, so watch what you say. My colleague Mark Perman is just going to run through a few welcome slides.
So we're all here to hear John talking about nitric acid rocket engines today. So been very much looking forward to this for quite a while. It's something I've been involved in as well. So, and of course, it's one of the fundamental storable propellants was one of the things that led to on-orbit propulsion. So it all leads into space. So if you can move on, Bob. So normal format for the day, 1400. You get this boring welcome from me, and we'll hand over to John about 5 past, and he'll carry on until we've finished, and then there'll be questions afterwards. If you could move on, please, Bob. So again, just a brief reminder, please join the BIS. The BIS desperately needs members. In my lifetime, during my membership of the BIS membership has gone down from 5,500-ish to 2,500 currently. It was down to just over 2,000 a little while ago. And then all us good people started running branches, and there was a bit of an uptake in interest in space by the UK government, and membership has gone up a bit. But I like to think of as the branches as driving the membership up. So we desperately need members. So if you're interested in the future of space, please join the BIS. It's a great time to join. You can now join and you can pay monthly. There's been a change, so you can pay monthly instead of once a year. So if you're a member, you get access to the videos, talks, lectures, symposium, conferences on the members area on the new website. There is a new website. Excellent magazines. There's a monthly newsletter, and of course you get we do free events, free to anybody. So so you've got the camaraderie of an enthusiasm of that. Please join the BIS. Move on. And with that, I'm going to hand over to John Harlow, a former colleague of mine and chairman of the branch. So with that, over to John.
Thanks very much, Mark. Good afternoon, everybody. A history of nitric acid. I don't call it the history because it's still work in progress. There's an awful lot still to be discovered as such. But I guess you chaps can relax a bit. This won't be a lecture on physical chemistry. I know that'll annoy Pete intensely, but never mind. So with no further ado, please, slide number 2. Thanks. Bit self-explanatory, this one. Many have been here before. I know Mark certainly has. I've taken avoiding action from such clouds as this, both in the UK, US, France, Iraq, and in fact, my backyard. So not to be recommended. It's really nasty stuff. Next chart, please. Okay, while you're reading the agenda, I'd like to just put a little bit of this into context in terms of what I put there in shorthand, really, in the text box. During Westcott's history as a Ministry rocket propulsion establishment, there were times when not only liquids, but also the entire establishment's existence was in doubt. And in fact, pertinent to this particular talk, I've shown 3 what I call break points that where this nearly happened. Number 1 there is senior management discussed whether to drop all nitric acid work in favour of work on liquid oxygen. This was prior to or at the beginning of what we know as the Blue Streak program, when we had a program called Delta, which was LOX kerosene, which stopped, of course, when Rolls-Royce had this agreement with Rocketdyne to bring the RZ designs over here. The second one was the restart of nitric acid in 1966, soon after the new superintendent liquids. This was Dudley Lewis. As soon as he took over as superintendent of liquids, there was a move to actually close down the whole of liquids division. And I think Dudley did very well to convince the senior management that liquids should stay. And he proposed a program which led to the packaged liquid test vehicle, PLTV, as you can see down there. That was about 1966. Third one was more critical in a sense, because prior to the Cheveline program, the existence of the entire establishment was in doubt. And I'd say this, there's no doubt that the establishment was saved by that one project. Anyway, that's a list of an agenda. It's a fairly full agenda, so we better crack on. Next one, please, Bob. Obvious introduction there. Why am I doing the nitric acid one now? Because there was an awful lot of work and papers published on liquid oxygen as one of the oxidizers and hydrogen peroxide as another. Hydrogen peroxide I'll shorten to HTP, it's much easier. On the LOX programs, we had Lizzie, which started effectively during the Second World War. Delta, I've mentioned, the RZ programs, the liquid hydrogen program as well. And with the peroxide HTP, we had the kerosene peroxide rounds that we flew an awful lot of from Woomera. The general purpose vehicle, which was white fuming nitric acid and methanol. We'll come on to that a little bit later. The Red Shoes program, Black Knight, Black Arrow, blah, blah, blah. So the number of reports going through what I've been researching, number of reports published and their dates could be used as a diagnostic, as a measure of activity as to what was going on at Westcott. And you might say the same could be true of using photographic data. And if this actually shows the highs and lows, which reflected the comments that you saw on the last chart. Now, personally, I started to put together a paper on nitric acid, and my rate of work on that and several other papers is pretty slow. But Mark, bless him, convinced me that I should focus a little bit to get a talk going. So this is where we are today. I'd like to just leave you with some points to ponder as we go through. Most of this work was done at or with Westcott personnel. That's the first point. Second one is the term nitric acid here. I apply to the red fuming version, red fuming nitric acid, unless I specifically mention white fuming nitric acid. The other general point I'd like to raise is that unlike many of the liquid oxygen and peroxide programs and engines, many of whom had pump-fed propellant delivery systems, all of the UK designed nitric acid systems and engines discussed here had a propellant delivery system that was driven by gas pressure. Next chart, please, Bob. Okay, why use nitric? Well, as an ex-chemical engineer, it's a bulk chemical readily available and quite cheap. It has characteristics that are well suited to being used as a liquid rocket propellant oxidizer. We mentioned the two different types, white fuming nitric acid, which is effectively 98% HNO3, that's 98% nitric acid with up to 2% water. Red fuming nitric acid is made up of nitric acid with variable amounts of nitrogen tetroxide, N2O4, dissolved in it or mixed with it. You can have up to about 40% of N2O4 mixed in with nitric acid. After that, you get phase separation. Both white fuming and red fuming are normally inhibited with a percentage of hydrogen fluoride dissolved in them. Now, this is true in the case of the US and the UK, but if you look further afield, particularly Russia, they experimented with a whole range of different inhibitors. They used iodine, they used phosphoric acid and one or two other things as well. Pardon me. The oxygen content of nitric acid is pretty good. It's on a molar basis, it's 76%. And white fuming has a density of just over 1.51. and red fuming has a typical density of 1.56. That characteristic I've given you is for earthener type 3. One of the problems with white fuming nitric acid is that when it's stored, it has slow decomposition. It suffers from slow decomposition, and this carries on and creates a high equilibrium pressure in the tank, principally oxygen. And sometimes this can be well over 100 psi, so it's not something that you would welcome in a system if you wanted it to have a long life. You'd either have to relieve it or you'd have to change to red fuming, which doesn't suffer from that. Okay, chart 6, please, Bob. Where to start from? Okay, I've given some World War II examples there. Can't really speak much about the USSR. Some people have done some very interesting research there, I know. Frank Molina, of course, has done wonders with it, or did wonders with his WAC Corporal. Got there, as I said, to extreme altitudes there. I can't vouch really much more for the success of things like Wasserfall. They had a fairly successful program. Of course, they did have one serious disadvantage, that the Allies were trying to bomb the hell out of them while they were putting this program forward. Now, the Soviets ended up certainly using nitric acid. They were very successful in using nitric acid in their ballistic missile programs, barring one or two major accidents. And the historians among you will remember the Netherlands disaster of 1960, when an SS-7 or Sassin, I think was the NATO name for it, blew up the second stage, blew up and took General Netherlands with it. So ups and downs again with nitric acid, but in the end they got rid of it. They got rid of all liquids and they went all solid. So that's a story of nitric in a nutshell for the USSR. Next chart, please, Bob. Okay, there's a couple of different shots. I showed 3 different designs of Wasserfall on the previous slide. There's 2 there, nice color renditions. So, okay, so no UK work undertaken before World War II, unlike hydrogen peroxide and liquid oxygen. I put a question mark behind no, because you know, the research hasn't gone that deep, but all the researchers that I've spoken to, historians that I've spoken to, and quite aged rocketeers, should I say, do not recall or have not seen any reference to work on nitric acid as a rocket oxidizer before World War II. Consequently, at Westcott, liquid oxygen started pretty quickly with Lizzie. Hydrogen peroxide was used on, was it B site, I think, quite quickly. But until the German engineers arrived in 1947, there was no work done on nitric acid at Westcott. 3 names there that pop up again and again: Bob Haggerty, Paparedo, and Carl Meyer, really key personnel in Westcott's story concerning nitric acid at Westcott. Now, the variety of suitable fuels, I put that down as a bullet point. The Germans investigated a whole raft of potential fuels, some of which were self-igniting when coming into contact with nitric acid. Some weren't. In fact, they also went into looking at different ways of igniting those mixtures that weren't self-igniting. And I was interested to find that substances like triethyl aluminium and triethyl boron, which are still quite widely used. In fact, they're used on Falcon 9. So they were investigated as well during World War II. So nothing's new in that sense. The bottom line there is that straight after the war, rather than bring German engineers straight back to the UK, quite a few of them were put to work by the Ministry of Supply at a place called Traun, which was a test site in northern Germany. But as far as I can make out from any of the reports I've seen of that time, the only work that was carried out on nitric acid was really aimed at design inputs for a gas generator. Next chart, please, Bob. Okay, bit of a map here. Starts 1947, really. On the left-hand side, you can't really take a timeline across this, but this is basically the family tree. From the test vehicle point of view, and Westcott, you've got nitric kerosene 1 there, and later PLTV, packaged liquid test vehicle, and of course across to, with PLTV leads directly across to the Chevrolet propulsion system, a twin chamber propulsion unit, TCPU. And we'll touch on the other 3 systems a bit later in the presentation. What I'd like to say here is that one of the unknowns at Westcott, and it may not be a big unknown, but one of the unknowns at Westcott was the amount of symbiosis there was between Armstrong Whitworth Aircraft Company and the engineers working on NK1. Every report, every meeting, minutes, there was a lot of discussions. They were kind of intimately involved so that AWA could in fact pick up at any time the NK1 program and continue with it. And in fact, only the other day I was discussing with Mark the fact that Armstrong Whitworth installed a liquid propellant test rig up in 6 site at Westcott. And I never knew that anything other than solids were ever fired at 6 site. So I've still got to investigate that one as well. Okay, next chart, please, Bob. So leading up to NK1, what have we got there? As I said before, early focus on those earlier oxidizers, LOX and HTP. CD and J sites were in common use at Westcott with nitric acid. E site came in later. E site started as an aircraft rocket engine test emplacement, working hydrogen peroxide. Most all of the early days work on nitric systems was undertaken on chambers no bigger than 500 pounds thrust. I hope you guys are okay with old-fashioned money there. I can't remember what 500 pounds is in newtons right now. Spoke on the focuses there. All the different aspects of systems that you could put together aimed towards a flight vehicle were investigated and in fact tested. And in fact, Westcott did some work with white fuming nitric acid with kerosene, and in fact this other mixture that was fairly new to me, WAF1, that's a mixture of amines. It's aniline plus furfuryl alcohol, I think 50-50. Now the text box at the bottom there, I've just put a requirement, the performance, overhead performance requirement for Sea Slug as issued by the Naval Staff Requirement. Unfortunately, and I know Peter's suffered from this a lot, it always seems to be the case that when you get a missile design, they fill it up with all the other bits apart from propulsion, and what you're left with is a volume, and you've got to get all the performance they want out of that volume, no matter how small. And NK1 was no different. So in the end, we had to live with 3,500 pounds thrust for 20 seconds. But whilst that issue was being addressed, they carried on flying with the reduced thrust time. Next chart, please. So NK1 was aimed against a Naval Staff requirement, Royal Naval Staff requirement for a ship-to-air beast called Sea Slug. The Sea Slug ended up being all solid, of course, as you probably well remember. But also there was an anti-ship version of it, sometimes called Blue Slug. Now, there were strong parallels, of course, with the kerosene peroxide that went on RTV2. Airframes were the same diameter. They were all gas expulsion using piston tanks, pressure fed, obviously. I've got there the first flight. Yes, that one appeared to go well, but most, as I put there, most ended disappointingly. We fired these from Aberporth. The first 6 were fired from Aberporth. As you see, one there sat on the ramp and just puffed away, and one was called missile test vehicle cold because it didn't have any nitric in it. It had all leaked away, but they still flew it off with the solid boosters just to get rid of it, I think, more than anything else. Next chart, please, Bob. Okay, the propulsion system there. Let's tease into that a little bit. On the left, you can see some gas generators. There's a kerosene tank with a piston being driven from left to right. On the right, there's a nitric acid tank with a piston that's being driven from right to left to enable a better control of the center of gravity and therefore control of the vehicle. That was pretty standard form, actually, of most of the liquids of any description. That's the liquid test vehicles of any description of the period. So that's NK. Now, if we go to the next slide, please, Bob. This one here is an AWA around. Thing I'd like to mention is that they've changed the fuel component there. Instead of it being kerosene, it's methanol. And you can see the change, obviously, by the different volumes of the propellant tanks there. But essentially, they're the same beast. And RTV2 was a very successful vehicle. In fact, nitric methanol was a lot more successful than nitric kerosene. Next, I put there many rounds for, an awful lot of rounds for 5 and 1. Next chart, please, Bob. Okay, so now we move on to PLTV. Now, this really was a technology proving program, just as well it was, because we needed all the technology that was involved with PLTV later on in the TCPU for Cheveline. Very successful. As I've got there, only one misfire, solid propellant gas generator misfired, and so they redid it and it flew very successfully after that. It gave us all the technology and the ideas that might have been needed if we needed to apply this to an air-to-air missile. And in fact, we'll just touch on one later on called Spartan, a Hawker-Siddeley device that used somewhat similar technology to this. Next chart, please, Bob. For those who like numbers, there they are. I think it's fantastic that we fired a quite low QE. I'm not sure that that's elevation, quadrant elevation. I'm not sure what they did. There was no boost. So to my mind, I don't know whether that's a true QE or a ramp QE. When it goes off the ramp, obviously you get tip off. The nose drops before the tail leaves the ramp. And it's a very low QE, but it gives you 6 to 7 miles range. And it landed effectively in the north end of Cardigan Bay. Next chart, please, Bob. So the next leap really was the TCPU, and Mark knows this beast very well. It was the last project involving nitric acid at Westcott. There were 1 or 2 problems. You saw a cloud on the second slide, and that's what happened after the firing that you see at the bottom right here. We can touch on the reasons for that. Blow-by was one of the big problems we had, and I'll tease into that a little bit on the following slides. But it was 6.4 kilonewtons, I remember that one in Mickey Mouse units, for a maximum of 13 seconds. There were 2 chambers. You can see with the yellow covers on the left-hand picture there. One chamber obviously had to burn twice, but only one chamber burned at any one time. The reason why there were burns like that is those nozzles were at different angles to try and make sure the thrust line passed through the center of gravity of the penetration aid carrier, which the TCP was moving about whilst in space, basically. So yeah, solid rocket motor competitors. I mentioned this on those of you who remember the lecture I gave on Cheveline. There were competitors for putting in an equivalent impulse for both of those liquids, liquid burns on the TCPU there. On the bottom right there, you can see OB13. That's an Ordnance Board trial. Long live the Ordnance Board. It's dead and buried now, guys, unfortunately. Nice, clean exhaust. But of course, when you get to WEP3, things start going wrong, or can often start to go wrong, and you end up with, I forget what Musk called his recent little pop with SN8, but it certainly, disassembly comes to mind. Next chart, please, Bob. Okay, let's tease through the TCPU here. Just let me run through the operation of it, and that might make it clear to everybody. Gas comes in from the left, big black arrow through burst discs A1 and A2, pressurizes the volume behind the pistons there. Now these pistons move outward from the center rather than from the outside towards the center. Now, in order to seal the pistons and stop the propellants reaching each other, and they were hypergolic, these propellants, there are a pair of lip seals. But obviously you don't want those seals in contact with things like red fuming nitric acid while the thing is being in store. So there are shearings at positions B. But once the pistons move and the force behind the pistons is sufficient to break the shearings, the lip seals actually travel over the broken shearing remnants. And that, of course, completely disrupts the seal, and some of the, shall we say, fuel and oxidizer can get into the volume between the two pistons there, and well, mayhem can result. So that was one of the problems that we had to address. But once those tanks are pressurized, propellant tanks are pressurized, the propellants are free to go down to the valve, and then one after the other of the combustion chambers on the right are operated for the length of time that the repositioning burn is required. Don't think I've missed anything out there. Next one, please, Bob. Right, okay, active TCPUs. I say active on TCPUs because we did fly quite a few dummies, certainly on 4-staff trials as well. There were 3 full-staff flight, well, there were more than 3 flights, but 3 full-staff flights that had active, fully loaded TCPUs on. Pad trials from Pad 29 at the Cape. I remember it well. Sunning myself on the beach down there. Shouldn't say that, of course. Working very hard. Some of those flights were successful, some were not. After that, there were 6 submarine launch trials, and followed by 17 demonstration and shakedown operations. DESOs are fired, or firings with a DESO occur when they change the cruise, or the submarine has a refit and it has to go out and do test trials and everything like that. They end up firing 1 or 2 or 3 of the missiles, and then the submarine carries straight on and goes on its mission. Being a liquid, of course, certainly with hypergolic propellants, their lordships of the Admiralty were quite worried, I should say, about the possibility of some of these liquids escaping, especially in a submarine, and creating mayhem on board the boat. Well, we had secondary containment and all sorts of sniffers around the tanks to detect any leakage. And I'm pleased to say, as far as I am aware, there were no emergencies encountered. We never had to get out in the early hours of the morning, run across to Faslane or anywhere like that to put out fires. So the system worked. Okay, so next chart, please, Bob. These are board-in systems. Okay, let's start off with the corporal. I think my memory serves me right. We bought 113 corporals. And there's a few interesting facts about the corporals there. FFA is for fuel alcohol. That combination was hypergolic. It was a 20,000 pound thrust engine, pump fed. It shows the range there. I heard it quoted, it was something like 12 hours to set up before you could fire it. No, it doesn't really, it's not a really good and flexible system. And you had to fire it from pre-surveyed positions, so that if the Soviets or East Germans at the time found out where your pre-surveyed position was and just lobbed a few even conventional munitions on that position, they couldn't fire the missile. Interesting point at the bottom there, the island of South Uist and the range at Benbecula was set up specifically to test and to train our army guys in the firing of corporals. Prior to that, they had to go to White Sands and do all the training and testing over there. Is it rockets galore? I think there was a film made about the islanders that didn't like the idea that their island would be used as a missile range. So if anybody gets a chance to see the film Rockets Galore, then there's a lot of similarity between what happened in Benbecula and the film. It's quite a laugh. Next chart, please, Bob. Stiletto. Okay, I had something to put. Sorry, corporal there. There was no input of Westcott at all. No input of the UK to any use or servicing of that system. Stiletto is different. Okay, Beach manufactured it. Went to Shorts in Belfast, and you might not believe it goes over 100,000 feet, but you can take my word for it. It goes way over 100,000 feet if things go wrong. Our involvement was to fill the beasts at Westcott and then ship them straight out to Lambetter. So next chart, please, Bob. Yes, dropped from a Canberra, taken off from RAF Lambetter, and then went over to Benbecula and flew out of down the deep range out of Benbecula. The problem we had was that on the highest flow setting for the dial-up Venturi in the propellant lines, the vehicle gave it far too high a thrust. So I was brought in to try and assess what the problem was. They didn't understand it, how it might be addressed. So I had some fun in Belfast. I had some fun. I didn't get to Benbecula, thank goodness. But I did get over to the States and to a place called York, which I don't know whether you guys know, but Harley Davidson have their manufacturing plant at York in the States. And I got a good look around the motorbike shop. I tell you, it's fantastic. We also fired a rocket motor, by the way, one of these rocket motors for Stiletto, but that was by the by. So what happened when the Stiletto was launched, going down the deep range, it was supposed to travel at a fixed height or a set height or series of heights at a set velocity or series of velocity, which were quite limited. And if the RAF came along with their Phantoms and tried to engage and the target was not behaving itself, then the fighter jockeys were not allowed to engage it. So we were losing effectively training on these overperforming targets. So we came back, and in the end, I think Malcolm Paul at Westcott and Frank Henderson designed a variable flow Venturi that was a drop-in device that you could put quite simply into the propellant lines, and you could vary the thrust at any time It was quite a simple modification, an obvious modification. United States Air Force were interested in purchasing it as well. But unfortunately, the MOD were not interested at all in any more modifications, and the RAF had to live with a much more restricted flight envelope for their intercepts. Next chart, please, Bob. Okay, again, something that Westcott had no input at all into. Filthy gas generator exhaust there, pressurizing the piston tanks inside the vehicle, the Lance missile there. The only work that Westcott were involved in was an attempt to gel the nitric acid, the earthner that was in these missiles. But after a long period, even with a genius chemist like Barry Mello at Westcott, we couldn't do it. So that was a shame. Okay, next chart, please, Bob. What else did we do? Okay. In the development of the PLTV, we ended up with Spud Injectors. We had a big program to try and design vortex injectors as a competitor to this type of injector, but Spud won out, and vortex, a lot of the vortex engines were used by RADI there to test as a test engine for re-entry materials testing, nose cone survivability basically. So they fired a rocket engine at the nose cone just to see what the effects of re-entry heating would be. Gel studies we spoke about, plume studies, Q-site. I don't know whether you Westcott guys realise that Q-site has been flattened now. It's another shame. I used to work out of that site as well, 247 building. Again, these are most important, and a lot of the plume work was run by RADI. The idea is that you need to understand how much attenuation you get of radio signals if you are looking up to a missile that's firing and accelerating away from you, because the strength of signal decreases enormously if you try and drive it through an ionized plume. Moving on to other serious studies there, as we said, the RTV2 sustainer using white fuming nitric acid and methanol. That didn't make it through to RTV2, if you like to say RTV2 in service, because that role was taken by a hydrogen peroxide and kerosene system. Harry Sunley, he did a little bit of work on a liquid Martel. Martel, for those history buffs, if you remember, was an anti-radiation, a French anti-radiation missile. But again, it only got through the study phase. We mentioned Spartan a bit earlier, the Hawker-Siddeley Dynamics organization tried to, I'm not sure how big the missile was, but it's about the same size as Red Dean, which was quite a large air-to-air missile. And again, this is more research is required in this area as to how far Hawker-Siddeley's got with that program. But they did have a license from Thiokol in the States. The Thiokol had some red fuming nitric acid and UDMH motor systems that were used on Bullpup A and Bullpup B. But certainly Spartan never got very far. And another one I'd like to bottom out also is Blue Water. There was a proposal for a liquid version of Blue Water. Blue Water 1 was a solid motor Saluki, I think it was, from Summerfield. Blue Water 2 was supposed to be Phoenix from Westcott, and that was a polyurethane solid propellant. And all I can assume is that the liquid would have been a Mark III, so that's hence the question mark there. Next chart, please, Bob. Okay, well, where does this leave us? Late start, always behind the curve. Yes, this was a quote from Alec Baxter, who was one of the early superintendents or bosses of Westcott. he put it down to being 2 years behind. Nitric acid was 2 years behind hydrogen peroxide, and unfortunately it stayed that way in a sense. Unfortunately for nitric, not necessarily for the rest of the world. In the end, solids overtook everything. So success eluded early systems. Yes, early flights were a disaster. Even at Woomera, when Armstrong Whitworth took over the NK1, the nitric kerosene design, and flew NKs, not under the NK name though, at Woomera, they had about as consistent failure rate as we did at while we were flying out of Aberporth. Way less successful than peroxide-based systems. So PLTV eventually, that was a successful system. It wasn't followed up with any other system after that, apart from Cheveline. Next chart, please, Bob. That's it. Well, I forgot that. Well, thanks very much indeed. Thanks for your attention. Any questions?
Well, thank you. Before we start the questions, thank you very much, John. That was a great talk. To ask a question, could you try and attract my attention and unmute yourself? I'm going to go to gallery view so I can see you all.
Hello?
Hello, Yeti and Bear.
Yeah, yes, I'm the Yeti, that's the bear. I was just going to say, I'm trying to sort of pick out of a lot of this, but was any of this tied at Spade Adams? Because I know that's where most of the UK rocketry stuff was, wasn't it? Or have I got that wrong?
I don't know of any peroxide work or nitric acid work that got anywhere near Spade Adam. It was all LOX kerosene.
Oh, right, okay. Did any of it get down to Cornwall, or is this all in other places?
Cornwall?
Yeah, because I heard there were quite a few they like launching rockets from there because they went off into the Atlantic and they didn't have to worry about finding them again.
Yeah, you'd have to worry about a whole lot of other things. Airlines and no, I don't know anything about launch sites of nitric acid from Cornwall at all. You're not getting muddled up with the Isle of Wight?
Don't think so. Was there stuff going on there, was there?
Yeah. Black Knight, Black Arrow.
All right.
All peroxide systems, by the way.
Yeah, because I know what was it? The Fancy was that torpedo that used peroxide that they kept blowing up their own bridges by mistake, and when they made a right mess down in France, didn't they, with them? Or have I got that mixed up again? I know that peroxide in torpedoes was considered to be something that you just don't go anywhere near because you keep it went so badly wrong.
Well, there were some compounds that were worse than peroxide when they used them in torpedoes, but we won't go into that.
Well, it was peroxide that eventually took the Kursk down, wasn't it? Or the Kursk.
Was it?
Yeah, that's the best theory at the moment for what actually happened on the Kursk or the Kursk, which is a Kula class or Typhoon class under NATO language. The Ruskies had decided that they'd use a peroxide as a propellant again, which was never really a good idea. And one of them, not the torpedo, basically fractured the tank. So it started spraying out onto all the copper components. And it didn't explode, but it exploded via just having too much gas in it inside the tube. And that's what basically singled the end of the Kursk. It was the only thing they couldn't effectively protect with its double shell. So if I'm going
okay,
off.
so next up, next question, Mick Droob, and then we'll do Rod Woodcock, and then we'll do Delta V Media.
How you doing, Mick?
Fine, thanks, John. Not so much a question as something to add to the Lanced missile. Myself and a couple of oppos when I was up at 32 site did some trials at B site whereby we this was for the Army Ordnance Depot at Kyneton.
Yeah.
And the deal was to unload the fuel first, which was about 1/4 of a ton from a Genetron, if you like. Strip the Haskell pump down, change the seals, put seals in that were okay with earthner, and then pump 1/4 of a ton of that propellant off. The idea being that if they had to detank the Lance in the battlefield scenario, they wouldn't need 2 detanking systems. And I have to say it worked. However, that wasn't much use because I think about 6 months later they withdrew the Lance from use. But that was some work that we did with the Army Ordnance guys.
Okay, thanks for that. Yeah. I didn't mention Malcolm and Wham-Bam going over and detanking Stiletto, but that's too long a story.
Yeah, yeah.
Okay, Rod Woodcock.
Right, John, could you explain, please, the difference and the use between HTP and nitric acid? Was it beneficial to use in some types of rockets and not others? Because it seems about that time, those are the 2 oxidizers that were being used. And could you explain why one was in preference for another on different missiles?
I mean, there's a whole raft of things you could go into there. I mean, how long have you got on?
It's storage. It's the storage of the propellants as much as anything.
It's long term. Unfortunately, see, peroxide decomposes anyway, but okay, you could vent that. Nitric, you know, you could put HF on it, but slowly you would see a sludge. Keep me honest, Mick. You would see a sludge build up, and you don't want sludge going through your propellant delivery systems, let alone your injectors. Every one of them has got their own particular issues. So I think with the people that we had when we started, and this is an opinion at the moment, the people we had when Westcott started, that was the technology that they were comfortable with, and that's how it started. Given that Lizzie was firing during the war, that was an obvious one to continue. That's lots.
The major problem with HTP, and still is trying to store it. As John said, it does decompose. The problem is if it gets, ideally you want around 80 to 90% purity to make it of any use for a rocket engine. After a time, if it gets below 70%, you might as well throw it away. It's very difficult to store. And this is, everybody keeps raving about it even now for use in space engines, but you still have the fundamental problem of trying to store it. As John said, with the nitric, you can put an inhibitor in, inhibited red fuming nitric acid. Bernard Bonner, who John will know very well, who was head of chemistry at the time, did a lot of long-term storage trials on the TCPU tanks. That they were life tests. I mean, they were stuck out in the field for years, weren't they, John? Mm-hmm. And we knew there would be a sludge there, and we did fire. I did fire, myself and Malcolm at eSite. We were doing the batch proof testing, and some of those tanks were, well, the propellant in them was of an age. That was the least of our problems trying to fire them at ground level. As again, John and probably Mark will know, because the buggers kept blowing up for the reasons that John touched on with the seals on the propellant tanks.
Thank you for that. Could you tell me quickly then, HTP then, the storage, what would you say would be a time when how long it could be stored before it started to deteriorate?
You're looking at It's got to be a reasonable room temperature, 21, but it really is a matter of weeks.
Right. Okay.
It will start as soon as you get it delivered. If we, the company I work for now, European Astrotech, we do a lot of compatibility testing with it. It's hard work because we have to start with the highest strength that we can, get whatever materials are going to be tested with it, and then see what happens. The problem we have is we don't know whether it's the decomposition of the propellant that's causing the pressure rise or the reaction with the material quite often. But the fundamental problem still is trying to store it.
Okay.
And it's weeks, you know.
Right.
But then again, if you're using it for the much mooted small launch vehicles, if you get it loaded quick, get the thing up there, you're using that propellant, you know, within a day or two. So that doesn't become a problem. But there are other problems associated with HTP if you're using it as a biprop, because it can be used as a monoprop as well, and that's where it becomes a very green propellant.
Right.
Because
I'll actually have another talk on that, won't we?
Well, yeah.
Just to mention, on the PLTV and TCPU programs, the long-term storage programs, we proved that the tank assemblies were good for 20 plus years.
Wow. Okay, Delta V Media.
Hiya, John. Yeah, I'm just wondering, in terms of specific impulse, what the differences were in these sort of propellants and solids. Because as Mark just said, I mean, you know, potentially you could store them for quite long periods. And I'm just wondering if, you know, if the differences between the efficiencies of those propellants was not great enough for them to consider it worth using liquids as opposed to solids for those sort of quick reaction type situations.
I'd have to go on, Pete. I'll let you answer this one.
I think the major problem associated with tactical systems was volume. And the difference between the density of a liquid system and the density of a solid system was such that we were generally volume limited, as John said before. Basically, they designed the vehicle and gave what was left to us and said, meet the spec with that. And so generally what killed off liquids, as far as I'm concerned, although there was a higher specific impulse, quite a considerable increase in specific impulse, it was the volume available in order to store the propellant that caused the move to solids.
Right. So I mean, you didn't get a significant enough greater range from the liquids to make it worth them sort of redesigning systems around that.
No, when you did the whole system optimization, then almost always solids won.
Yeah. Thanks.
There was also a great deal of nervousness amongst the services about liquid propellants.
Yeah,
I think.
Yeah, I didn't know whether to mention this or not with regard to Cheveline, but when I was assistant director, I think it was, then I always had to carry, John, I don't know whether you remember this, I always had to carry a document called the Primrose document with me.
Correct.
Yeah, and so whenever I went, I had to have this in my suitcase or in my briefcase, just in case something went wrong, and that was due to the concern primarily of the liquid components in the system.
That's correct. I don't know whether you were on that as well, Mick, but I was on it. Ron Bellis, quite a few people were on that list.
That's the first I've heard of that name, Primrose, but I was on the legendary detanking team. But that didn't move 1 inch.
There you go.
I mean, the fundamental problem, as Pete alluded to, was the thing is solids are simpler. That's a very broad statement there. You know, it's a firework. You fill it up with propellant.
How dare you?
I knew you. Well, that can only come from the liquids, man. You'll understand what I mean. You know, it's propellant and then igniter, whereas a liquid system, there's valves, there's things mechanical that can go wrong, and it's the overall cost that does come into it as well.
Mick, you should have quoted Von Braun, quick and dirty solids.
Yeah, well, there you go. Enough said.
Yes,
it's the complexity of the liquid systems that would have added to the preferential use of solid. Plus,
I think with regard to the Primrose system again, it always amused me the fact that I think it was the solid side that I was concerned with. It was if anyone rang me up and said, we've got something ignited, what should I do? My attitude would be run like hell, basically. There wasn't a lot you're going to do.
That's right. Well, it would have been too late by the time we got there to do anything anyway.
Absolutely.
Yeah.
Does anyone...
Ideally, we would have followed the transport of the TCPU from Westcott to Coalport, but that never happened. We had a Land Rover that went at about 50 miles an hour maximum, so you'd never get there in time. However, it never happened.
Didn't you drop one off the back of a lorry once, I thought?
Not me personally. Somebody might have taken one home with him after we'd fired it. I didn't say that. And it wasn't me.
It's the one in Mark's garage. Okay, next up, Steve, I think you've got a comment you wanted to make.
Yes, hi guys. John, thank you for that interesting talk. Very interesting. I just had one comment about Martel. You quite rightly stated, John, it was anti-radiation missile, but the name came from maritime television, and there was a second option, which is television guided. Interesting, I didn't know there was a liquid project for it, and it's interesting to know that in the 1980s, Hawker Siddeley Dynamics developed another missile called Sea Eagle using the same airframe, which is, I think, still flying with the Fleet Air, I'm not sure. But that was then moved over to a turbine engine. So they kind of went in the direction, no, it isn't a rocket motor, but interesting to know that, you know, they were going for a longer cruise performance and kind of thing. So interesting. Thanks very much.
Okay, next
all
week.
in answer to that is that you'd have to look deep in the archives in Coventry to get Harry Sunley's reports these days.
Okay, thanks.
Could I tell you a story about the archives at Coventry? You remember we had the databases that that were supposed to be recalled but weren't, Mark. And I had occasion that I wanted to reference them, so I rang up the Rolls-Royce archive at Coventry. I said, "Could I please have the copy on this particular motor?" And they said, "No, I'm afraid, Dr. Penny, you can't have it. It's classified." And I said, "Yes, I know. I'm the one that classified it, but I still can't have it."
Which one are you missing, Pete?
Yeah. The hidden story is that I gave instructions to everybody they should return all of these databases to me. There are plenty out there still.
And some of us didn't, did we?
No.
Okay, I've got another question from Yeti. He's asking if there's any future for nitrate, John.
Yes, in the chemical industry.
Rockets, I take it.
No, it's all MON.
Yeah.
MON
Just
all going on to green.
Right, mixed oxides of nitrogen, if you don't know what that was.
Yeah.
I think it's worth saying that the experience gained on these early systems in the 40s, 50s, and 60s, the design experience, the design codes, how to test them, all enabled things like the work on MON systems now. So we know how to design an engine of that type. So things like the Leros engines, and a lot of the other on-orbit propulsion systems, you can find the design practices go back to these storable propellant rocket engines that were developed.
Do you reckon, I mean, these days there's a lot of discussion of basically non-rocket based, propulsion systems with actually within space, the idea of ion thrusters and all the rest of it. Do you think this is ever going to go completely forward, or are we still going to be dependent on essentially rockets to get to space, then trying to come up with clever things to do us once we're in space? Or do you reckon we're ever going to go any further to move completely to non-chemical essential propellant systems, if I'm making any sense at all?
It depends on the application. The problem with ion engines, I worked on those at, as it was then, Astrea and Portsmouth.
Yeah.
And those engines were Russian for north-south station keeping on the Eurostar spacecraft. They only used them if the mission life was over 15 years. The problem being those ion engines are extremely heavy. You need, with redundancy, each pack one side was 50 kilograms. So there's 100 kilograms, one for north, one for south. The power system for it that made the thing operate was about 150 kilograms. Then it's the amount of electrical power you need to make them work. So if you've got a huge telecom spacecraft with spare capacity in terms of electrical power, then you can use them. Bearing in mind that a telecom spacecraft is there to do what it says, telecommunications.
Yeah.
So it becomes a trade-off between the chemical systems, because you can do north-south station keeping, attitude control with monoprops or biprops, small thrusters.
Yeah.
Electric propulsion will always be more efficient. The problem is the thrust levels. There's a hell of a lot of development work going on in electric propulsion, and not only with and there's various forms of ion engines. The smallest of them really just being a small sheet of Teflon. You put some volts across that, it ionizes the Teflon with magnets there. You accelerate those ions and produce an incredibly small thrust. Now they're being used in CubeSats at the moment to maintain altitude and therefore the life. But it's still a trade-off from a financial point of view and a mass point of view. The problem with your most efficient chemical, well, they're not even chemicals, your most efficient liquids are your cryogenics, but you can't store them.
Yeah.
And the problem, if you're going for deep space missions, this is where you have to think about electric propulsion, or indeed nuclear, which has been around for decades anyway, because you have no power from the sun. So any deep space probes are using nuclear systems anyway.
Yeah, it'd just be nice to think that we could get to the point where we weren't reliant on basically throwing things out the back to make things move forward.
Well, I mean, there's other ways of steering spacecraft. You don't need thrusters. You can do that with magnetorquers and wheels, which they do.
Yeah.
So you don't need thrusters. But again, it depends what the application of the spacecraft is, how big it is.
Yeah.
The very simple propulsion systems, when I was at Surrey Satellite, for orbit maintenance, we were using they still use them, butane thrusters.
Oh,
camping gas, and it's just heated up. The thruster is a tube with two heaters in, made Bognor Regis of all places. You just heat the gas up. You don't ignite it, but because you're expanding the gas, that's at 2 bar pressure, nothing. It's vapor pressure. It's enough to maintain the orbit of that spacecraft. Yeah. You keep it as simple as you can. As I say, it's all about the application, and you have to have to differentiate between spacecraft and launchers. Launchers, you can't do it. Launchers, you can't do with anything other than liquid, solids, or cryogenics at the moment. EP will never work.
Yeah. So what was this thing with you just use a Teflon sheet and apply voltage and it will so that's Southampton University. They've been doing that for 5 to 10 years now. It's a small slab about 20 millimeters by 20 millimeters. A guy called Pete Shaw, who was at Surrey, he's now at Kingston University in charge of their propulsion section. He did a lot of work on that. But it's a small slab of Teflon, some small pointy thing pointing at it. You zap it with a relatively high voltage, it ionizes the Teflon. Yeah.
Those ions are accelerated, and there's your thrust.
Right, so that is it throwing bits of the Teflon off, or is it literally just pushing against?
No. You're just ionizing the constituents of that Teflon. Those ions are, if you like, initially free floating, but you have magnets in there, positive, negative, that accelerates the ions out, which is the same method with krypton or xenon on the gridded iron engines. The problem with xenon, now is it was always expensive. It is now horrendously expensive. So what the spacecraft primes are looking at is using krypton, which isn't as dense. The ISP isn't as good, but it's good enough. It's a question of cost.
I know that for Persephone, the problem was for Persephone was if they actually had enough xenon thrusters, they'd actually use up the entire world supply of xenon.
Well, there you go. Yeah. And of course, you see xenon's used in the microchip technologies. You have xenon lights on cars.
Yeah.
Used xenon is even used for double glazing now. There's a huge market for it.
It's nice stuff.
Okay, so hopefully moving back onto nitric again. So Robin Brand, you've got a question.
Yes, indeed. Thank you, Bob. And thank you, John, very much for your talk. Most interesting. I'm glad you managed to sort out your internet communications. Okay, moving on to the present day activities, if we may. Mark Perman mentioned earlier that Robin Haig of Sky Aurora will be coming along to give a talk or doing one online. And if my memory serves me correctly, they're using HTP and ending up with a 3-stage vehicle rather than using LOX as an oxidizer. And so I was wondering whether any of our experts here could sort of give some comments on whether using HTP is a wise engineering choice or what the case may be. Silence.
Well, the jury's out because all Becks are keeping a lot of their activities.
Yeah, this is Sky Aurora rather than Norbex.
I won't go into Sky Aurora. I've had dealings with them, so we'll leave that one aside for the moment. All Becks are keeping their activities very much to themselves. If they choose to use HTP, fine. Again, it comes back to this question of storage and getting hold of HTP. There are probably 2 manufacturers of it worldwide. One's in Germany, the other's in Russia. I suspect the Chinese have got it. Any movement of large quantities of HTP pricks up the ears of governments. And the Bloodhound team, the world record attempt, for the fastest car, they ran into that problem. They wanted 15,000 litres and were told no. The problem is HTP, if you mix it with chapati powder, makes a very good bomb. And so governments get quite excited about moving that amount of propellant around. So that's the first problem. I'm sure Orbex have overcome that one, but they would be getting it from the German suppliers. It's down to whether the German suppliers can produce those amounts and transport it. That's the big problem.
Is there any possibility of manufacturing it in this country under government auspices?
Yes, because again, we at EAL have done that. It can be done.
The problem is it needs to be a demand for it from this government.
Exactly. The government
or from private enterprise.
Yes, the industry. It can be done. We did a pilot scheme 2 years ago at Westcott on B-side, which is where we're based. And we took, I think, we took 6% hydrogen peroxide, which is what the ladies use to bleach their hair. So that's commercially available anywhere. And then basically you distill it. You just keep distilling it and up in the percentage until you get to a minimum 75, 80%. But it takes a long time. And you need a very big distillation process, a system to do that. But it can be done. Then you've got the problem. The fundamental problem still comes down to storing it and shipping it.
All right, we have some questions now about first of all, Rich Newlands is asking, are there any issues using nitrate with turbopump seals? And before you answer that, we've also got Alex Wood. He's asking, how did you solve the problem of broken sealings damaging the lip sills?
You file it and be damned. To be honest, certainly with the third repositioning burn on the penetration aid carrier, the requirement for reliability was something like 30%. The real need for Rep 3 was to get the pack out of the threat cloud, just put it like that. You didn't need to, but nice to have, I think, was the requirement on Rep 3. But you live with it. If you're in space, so what?
And you have to think about what the thing was actually being used for.
Yes, there weren't any coming back.
First two burns were the critical ones. The third one just caused further havoc, which was the whole point of the system.
Okay, we have another question from Alex Wood. He's asking about the corporal and why it had to be fired from a pre-surveyed location.
If you don't know where you are, how the hell can you hit the target? We're not talking days of GPS, way before then.
Okay.
But wasn't that a problem for every kind of rocket? Why was it specifically you mentioned it for corporal?
Oh, and ballistics, this was, yeah. When silos and submarines know their position very accurately. They're pre-surveyed.
But again, the silo, the submarine systems came in later than Corporal. Corporal was pretty much a first generation American ballistic missile, and each system that's come along has had better guidance, and it's meant that things got a lot easier and
that's true.
Less manpower.
That's true, but there was SINS. If you look at the history of ship's inertial navigation system, which was fitted to US submarines, you can go right back to Snark and some of the early, is it Snark? Mace? Some of the 1960 vintage.
Loon as well.
Yeah.
I think during the US submarine launched missile at that time was Regulus.
Oh, Regulus, okay, yeah. But sorry, I'm just going back on SINS. SINS has been used way back.
But that would be the missile that would use SINS on a submarine.
Yeah.
Just jumping in, Steve's message that the V2 was also launched from pre-surveyed positions. I think I understand why. So
but I just got a quick question regarding, well, why couldn't you just take an ordnance survey map with you? You'd know precisely more or less where you were.
Precisely enough. How big a payload have you got, Bob?
So you're talking to me?
Yeah.
Well, basically, I'm basically saying, you know, whatever you've got, you trundle up to anywhere and stopped. You knew very well where you were with an ordnance survey map. Why do you need to survey where you are?
Because a lot of the launches were in Germany, and you wouldn't necessarily have the same standard of mapping, I suspect.
That's the answer then.
The other way of actually launching would be to use the star systems.
Yeah. Okay.
Okay, next up, I've got it's a comment from Richard Newlands, who's saying that when we were talking about peroxide, he said a lot of American amateurs have had explosions distilling peroxide.
Yeah, you have to know what you're doing, I believe.
Yeah, I mean, even E-site at NASA Stennis, I don't know how many, wasn't that long ago, they had a site tank blow up with peroxide in it. And those guys ought to know what they're doing.
Yeah. It's not nice to, it's nitric I've handled, I've handled many propellants. HTP is not nice to handle. Of course, you've got all your splash suits and whatever PPE you need, but you have to be very careful with it. It's not nice. It's not, none of them nice, but at least you understand how to use them. HTP is a bit of a problem. Any leaks you get, if you get a nitric leak, you know how to handle it. HTP, not nice, not nice.
Is it my memory? But is it that I remember whenever we used to take a shortcut to the canteen, we always used to put a hand on the HTP tanks to see whether they were warm or not as you walked by.
Yeah, that'd be quite possible. Yeah. They would be warm because of the decomposition.
Yeah,
it's quite funny. I can remember going to Charterhouse and chatting to some of the HTP guys, and their attitude was, HTP's fine, it's really lovely stuff. Wouldn't touch that nitric acid or Mon stuff, that's horrible.
Yeah, that's what they told me, Cliff Maidmont and the Black Arrow guys.
That's the same attitude I have towards liquids in general, actually. If I put a solid propellant on the table, it stays there.
Funnily enough, solids, Summerfield, were much the same about composite propellants. Summerfield specialised in double base propellants, and their attitude was, "Whoa, don't want to go near composites. Oh, horrible stuff." It's sort of what you know.
Yeah.
Courses for courses.
Courses for courses. Going back to HTP though, one of the things that attracts people about it, apart from its relative density, is because it's not a cryogenic liquid. You don't have all the cryogenic handling problems that you have with LOX, and so that is quite attractive to a lot of people, I think.
I think going back to the question about solids and liquids, perhaps I didn't make it clear that not only are solids got a higher density, but if you looked at the diagram of PLTV, then look at the gap that's there for the gas generator and the pistons. All of that in a solid system is full up with propellant.
Yeah,
I think blimey, I've forgotten it. Waxwing had I think we were just over 96% of the total mass being propellant.
Yeah. Again, that's what I was saying, Peter. It's the complexity of the liquid system.
Yeah, absolutely.
Going back to Mark's point, one of the things I've heard is the fact that if you're designing fuel tanks and you've got a cryogenic material, you have to insulate between the fuel and the oxidizer, which doesn't happen if you're using HTP. Whether that's a real engineering problem, I just don't know.
One of the ways of approaching this which has never really been developed in this country, to my knowledge, is the hybrid system, which depends, again, from what Mick was saying, again, depends whether you're on side with it. It either contains all of the advantages of solid and liquid or all of the disadvantages of solid and liquid, depending on whether you want to develop one or not. But I don't know whether or not Earthner was ever considered as being oxidant in a hybrid system or not. I'm just not aware of that.
Yes.
I'm quite au fait with hybrids. I've built a few. I haven't actually heard of, I've never heard of Earthner or nitric acid being used in a hybrid. Everybody goes for nitrates
They
because
have
it's a fad at the moment.
Tanks, the tank system.
Ah, right.
Like the tank gun, liquid gun.
LPG, liquid propellant gun.
There was a successful Earthner hybrid program done in the latter days of Westcott. Barry, well, in fact, I was peripherally involved on the igniter for it, but Barry Mellor and Roger Hull were involved in it.
Pete Boschko developed one at Summerfield. Went over to the States to get some development money from it.
The problem with hybrids, sorry Rick, is that their performance is a bit iffy. The people think they're going to get wonderful performance out of them, and they don't.
You have to work hard at it. It's not a given.
Certainly, looking at it from the design point of view, the mapping of the oxygen fuel ratios that you're allowed to work with hybrids limits you significantly over the performance you use for certain for applications. If the people give you a system spec for it, I found that when I was designing them that I couldn't use them where I wanted to simply because of this OF ratio problem.
Yeah.
That
regression rates are poor as well, so you get you can't get the high boost profiles that a lot of missiles want.
They're about 5 times higher than they used to be, but yeah, the OF ratio is a big problem, especially with liquid oxygen. It's a very peaky curve.
Yeah, going back to the Bloodhound car again, the highest thrust hybrid fired in the UK was one that was developed for the Bloodhound car, wasn't it?
Probably, yeah.
Yeah, Falcon system at Westcott.
All right.
And
again, it's all down to the application, isn't it? If it's for a missile, so fire and forget, solids will work. If you're looking at space applications, you might want to restart. That becomes a problem for solids because you can't. It's all down to the application.
We've got a question from Delta V Media. He's saying that Virgin Galactic use a hybrid system. Does anyone know what propellants they use?
Yeah, I do. It's not a hybrid. It's actually a tribrid. It was supposed to be nitrous oxide and that ghastly rubberized plastic that I can never get the acronym right.
Well, HTPB, was it?
Thank you.
HTPB, yeah.
That was just a fad thing with early hybrid designs. People had this stuff lying around. They used it on Spaceship One, but it kept chunking large chunks out the nozzle, and the pilots thought they were going to die. They've insisted on staying with it, but they've been having performance issues. They made the classic mistake of designing the aircraft and the motor at the same time. And so Branson's had to redefine where space is to his own personal lower limit. But what they're doing now is they're injecting a liquid into the post-combustion chamber just forward of the nozzle. Is it butane, something like that? It's a hydrocarbon to try and stabilize the OF and make the burn less violent and basically get the ISP up. But he's still calling it a hybrid, but it isn't, which is a little bit dishonest.
Thanks. Okay, we get another comment. John saying that back to nitric acid, that some American amateurs are still using white fuming nitric acid with turpentine.
Why not?
Why not?
The French used it years ago with some of their early liquids. That's why they didn't suffer any combustion instability, or not as much as we did, certainly.
It's the advantage that it's hypergolic.
Yep.
Along with furfuryl alcohol, which is the other one that's used.
Yeah, FFA.
Dense fuel.
So can
Okay,
I give
I'm
a
about to
plug
wrap up.
for
Mark.
Bob, can I just give a plug? If you're interested in propulsion, the June talk is a combined cycle propulsion system, which is a hybrid and ram rocket. So so that would be rather interesting, and we can continue the discussions on hybrids and so on. And another thing that came up was nuclear propulsion in our chat today, and of course the Scorpion talk in, I think it's March. That involves nuclear propulsion, so a nuclear propulsion tug space vehicle. So do come along for those. Bob, sorry I interrupted you.
Thanks, Mark. I was just going to wrap up. So we've just got one more comment I'm going to read out. It's from Robin Brand, and he's saying, solids require a specialist factory for manufacture and filling. So when Bridgewater closed down, that was the end of Raven Motors for Skylark. And you say no, Mark.
The one thing about solid systems is that the manufacture of the propellant is fairly simple. You can use the new development. There are these things called omni-rams, which use acoustic mixing, and they can be done in small buildings with just the normal arrangements for explosive limits in it. So there's absolutely no need in order to have specialist factories for this. If you want to fill a motor, the one thing you can do with HTPB systems is don't fill it in one go, fill it in a series of goes if you want. You can also make a thing called premix, which is the propellant without the isocyanate added, so that you can store that and then make what you want when you want it. So there's absolutely no reason why you shouldn't be able to develop relatively sized rocket motors, solid propellant motors very easily. Okay, if you're going to go up to Titan for boosts or space shuttle boosts, then over at Wasatch, then you see them having basically railroad cars tipped into the top of the propellant. And of course, if that's the size that you're talking about, then sure, you need very specialist equipment in order to do that. For normal size systems, certainly up to Raven systems, can nowadays be made relatively easily, I would say.
And just to mention, I think what Robin's thinking of with the shutting of Bishopton, the last batch of Skylark hardware, the production hardware, production filling was done at Westcott, the last production batch.
And that's plastic, of course. That's plastic,
yeah, that's plastic,
which is a very, very different system to HTPB systems. It's got its advantages and disadvantages. I always remember taking an American around Westcott, and we pressed the motor and said, "Okay, we'll fire that later." And he said, "What? You're not going to wait a fortnight in order before you can fire it?" No, we can fire it tomorrow. And he couldn't believe that. HTP is a very, very different, much more convenient system than plastic ever was.
Yeah.
Apologies for insulting HTPB. It's not. I do apologize. I've just had very bad experiences with hybrids.
The trouble you have, Rick, is that you're trying to use a rubber that is used in solid systems when it's not really appropriate for hybrids.
I couldn't agree more, Mark.
Much better things to use in hybrids.
The blood. I'm surprised this. The Bloodhound hybrid, if I recall it right, uses HTPB, HTPB combination, and that worked very, very successful on every firing. Never a problem.
Mm-hmm.
It's kind of a fad. A lot of the early hybrid guys were also solids manufacturers, and they literally had a lot of it around. So everyone in America just assumed that because they were doing it, it was the best thing to use. And certainly it's moldable, but mechanically it's really not up to the job. It's easier to use plastics, but obviously they're literal plastics like nylon. but they're more difficult to manufacture, obviously. Unless you 3D print them, there's been a lot of new research in 3D printing fuel grains, and it's working extremely well.
I think we'll agree to disagree. I think if we chatted about that, and Pete and I and you chatted about that, I think we could convince you of other things, but that's not for here.
Okay, so I need to draw things to a close now, everyone. So we're not actually running over our time frame. So I'd like to say a big thank you to our own John Harlow for putting on this talk on nitric acid. Rocket Motor is really good. Thank you very much.